Okay, so of course I would like first to thank the organizers for the invitation to this conference. So I'm going to speak about this, so about critical points of the Ambrosio-Tortorelli functional. So this is a joint work with Vincent Millot and Rémi Rodiac from Paris. So this is a first very basic slide about the Mumford-Cha and the Ambrosio-Tortorelli functionals that I think many of you already know, but I will quickly review about what I need, at least to fix notations. So the Mumford-Cha functional, where is the pointer? I don't see it. Ah, okay. So the Mumford-Cha functional, so which is defined here. So it is defined on the energy space called SBV2 that we've already seen in several talks here. So, but in few words, these are BV functions with no counterparts. And the smooth part of the gradient that I denote with an nabla U here is assumed to belong to L2, okay? And the jump set JU should have a finite area. So this is the energy space. And there is a well-known phase field approximation of the Ambrosio-Tortorelli functional, which is defined here, and that maybe I'm going to write on the blackboard to have it written for the whole talk. So the idea of the Ambrosio-Tortorelli functional is to replace the crack by a phase field variable that I call V. Okay, so you have an energy. So does it stop at some point? Yeah. So you have a phase field energy here, which looks like a Modica-Mortola type approximation of a sharp interface energy. So it looks like that. So if you only consider this energy, the phase field variable V wants to be identically equal to 1, because this is what minimizes Great. So this energy wants V to be equal to 1 everywhere because it makes this energy minimal. But there is a coupling term between U and V. So U is the same than in the Mumford-Cha functional. And this coupling term makes optimal that V should not be equal to 1, but to be equal to 0 in the portion of the domain omega where the gradient of U is not 0. And in particular, the gradient of U is allowed to be very large, and in that part, V is intended to be very small. So roughly speaking, V, the phase field variable, wants to be equal to 1 everywhere in the domain, except where the gradient of U is very large, which means where U should experience jumps. Okay? So this is the Ambrosio-Tortorelli functional that I call A epsilon of U, AT epsilon of UV. Okay, and one very good thing about this functional with respect to the Mumford-Cha functional is that it doesn't involve singular fields because U and V, so this energy is now well defined for fields U and V, which are in the Sobolev space H1. Okay, and the connection between these two functionals has been done by Ambrosio-Tortorelli, which tells you that the Ambrosio-Tortorelli functional gamma converges to the Mumford-Cha functional, provided this small parameter here is small enough, but in the sequel I'm going to forget about it. And as a consequence of this and of the fundamental theorem on gamma convergence, you get that global minimizers of this functional will converge to global minimizers of the Mumford-Cha functional. So V will always converge to 1 everywhere in the domain because of this energy term. So, but U epsilon, so which is one minimizer of this functional, will converge to a function U, which will be a global minimizer of the Mumford-Cha functional. So the Ambrosio-Tortorelli functional is much more pleasant from a theoretical point of view because the functional setting is much more easy. It's much easier than for the Mann-Forcha functional. But if you really want to compute minimizers, it's not that pleasant. And the main problem is this coupling term which is here, which makes this energy non-convex. And when you want to compute minimizers, numerically compute minimizers of a non-convex function, you may have troubles because classical gradient type methods should not converge to a minimizer. So an idea to overcome this type of difficulties is to use a so-called alternate minimization algorithm, for instance, used by Blaise to catch, okay, not minimizer, but at least to construct a sequence of competitors, let's say, for this functional, which makes the energy decrease. So the idea is that you start from an initial configuration, U0, V0, okay, and then you alternatively minimize your functional with respect to one of the variables. So for instance, in this first step here, where is it? Okay, in this first step, you fix V at the previous step, Vi minus 1, and you minimize with respect to U. So when you fix V and U, so this term is a constant, you minimize with respect to U. This is a perfectly strictly convex and differentiable functional. You get a unique minimizer. You call it UI. Then you plug it into your functional. So now you fix UI and you minimize with respect to V. This is again strictly convex and differentiable functional. You get a unique minimizer that you call VI. Okay? So I'm using here Dirichlet boundary conditions for both U and V. So you iterate, and then by some kind of fixed point argument, you show that your sequence UI VI will converge to a so-called critical point of the Ambrosio-Tortorelli functional, which will be a solution of this system of elliptic PDEs. Okay, so it's not in general a global minimizer because the energy is not convex with respect to the pair U and V, but it will be a critical point. So a point U epsilon V epsilon, which makes the Gato differential of this functional to be equal to 0. So this is a system of PDEs. You have two equations and two unknowns. So the first equation, in the first equation, the main unknown is U epsilon, but you have a coefficient here which depends on V. And for the second equation, the main unknown is V epsilon, but you have a source term which depends on U, and strong in a very bad way because this is an L1, it has an L1 regularity. So this is the critical point of the Ambrosio-Tortorelli functional, and an additional information that you have is that the Ambrosio-Tortorelli functional of such a critical point will be uniformly bounded with respect to epsilon. So epsilon is a small parameter. And this is essentially because this algorithm makes the energy decrease. Okay? And the question now is what is the asymptotic behavior of such critical points? Okay? Which again might not be a global minimizer because of the non-convexity of this energy. So this type of the claim is so you have the gamma convergence, AT epsilon gamma converges to the Mann-Forcha functional. The claim would be that critical points to the Ambrosio-Tortorelli functional will converge to critical points of the Mann-Forcha functional, whatever it is. But unfortunately, there is no general theory which tells you that such a statement is true, and you have to do it by hands for your problem. And this type of problem has been studied in many similar situations, starting from the solution of the Hennenfent equation. So it has been proved in various settings that solutions of the Hennenfent equation, so critical points of the Modica-Mortler functional, if you want, converge two critical points of the perimeter, so the gamma limit of the Modica Mortola functional, which are minimal surfaces, and this correspond to various works, essentially from the school of Tonegawa and his co-authors. Similarly, for the Ginzburg-Landau equations, there are several papers which shows in several situations the convergence of the solutions to the Ginzburg-Landau equations to stationary harmonic maps, and these are various works along the school of Bétuel, Brézy-Célin, Orlandi, Sandier, Serfati. For the Ambrosio-Tortorelli functional, the literature is much poor because there is up to now only two works actually, one from Francfort Les Serfati and another one by Les, which studies this type of problem only in dimension 1. And our objective was to try to generalize the result to any arbitrary dimensions. What we partially did, provided suitable assumptions that I'm going to detail. Okay, so, as I said before, the claim is that critical points will converge to critical points. But we have to specify what it means to be a critical point of what could be critical points of the Mumford-Scherr functional, and this is the object of this slide. So there are essentially two known ways, let's say, of doing variations of the Mumford-Scherr functional. The first one consists in doing outer variations, that is, variation in the state space, in the space where your function is taking its values, and it, roughly speaking, consists in computing the Gato differential of the Mumford-Scherr functional. So you take a test function phi in your energy space, and you do a variation of the form u plus t phi. So the jump set of phi has to be contained in the jump set of u because for lack of differentiability of the surface term in the Mumford-Scherr functional. And when you do that, when you do this type of variations, what you get is that the approximate gradient of u is divergence free. Okay, so this is not a Laplacian because this is the divergence of the approximate gradient. And in a suitable weak sense, because Ju is in general not smooth, that the normal derivative of u vanishes on the jump set. So this is a first type of variation, but it's not very interesting, or it gives informations, but that's not very interesting because by doing this assumption on the jump set of your test function, you are essentially not moving the jump set. So a way to make the jump set move is to perform so-called Heiner variations, or shape derivative, if you want. This is connected. And to do that, you take now a test function, which is capital X, which is now a vector field with values in Rn, compactly supported in omega. So in this talk, I'm not really taking care about the boundary. Okay, so everything, I'm not looking at the boundary. So you fix capital X like that, and you look at the flow generated by this vector field. You call it phi t. So this is a solution of this ODE. So it's known that it is a smooth diffeomorphism from omega onto itself. And what you do is that you compose your function u with the inverse map of phi t. Okay? You look at its Mumford-Scherr energy, and you compute the derivative with respect to t, the parameter t, at t equals 0. So this is a quantity that I call delta ms of u at x. So this is the Heiner variation. This is just a notation. And you ask this to be equal to 0. And this is a computation, which is not that difficult, that is possible to do. And this condition is equivalent to the following condition. So you have a first term here, which is bulk type integrals on omega, which involves the smooth mass of the gradient, and a term of the boundary, which involves the tangential divergence on the jump set of the vector field Ju, which by integration by parts is nothing but a weak form of the curvature of the jump set. And this has to be equal to 0. Okay? So this is first inner variation, you ask it to be equal to 0, and it gives a notion, a possible notion of critical point of the Mumford-Shah functional. So these are very well-known facts. And so we would like to prove that our critical points of the Ambrosio-Tortorelli functional, so solution of this PDE, of the system of PDE, converge to a critical point of the Mumford-Shah functional in this sense. So here are our first assumptions. So so as I told you before, so my parameter eta epsilon now, I forget about it. It's not relevant for the analysis. So I take a solution to this PDE, okay, with Dirichlet boundary conditions, okay. As I told you, I don't really care about boundary conditions here. And I assume that my Ambrosio-Tortorelli functional associated to this U epsilon V epsilon is uniformly bounded. So we first use the standard compactness result for the Ambrosio-Tortorelli functional, which was already contained in the work of Ambrosio and Tortorelli, which tell you that up to a subsequence, you can find a limit function U in the energy space of the Mumford-Shah energy in SBV2, such that U epsilon will converge to U, and V epsilon will converge to 1. Okay, this is again thanks to because of this energy term, and the coupling term V epsilon U times grad U epsilon will converge weakly to the approximate gradient of U. Okay, and there is another important quantity in this type of problems, which is the function W epsilon that I write here, which is V epsilon minus V epsilon squared over 2. Okay, and we can show that the gradient of this function will converge to 0 weakly in the sense of measure. And again, using the gamma lower bound for the Ambrosio-Tortorelli problem, we can prove that, okay, the first inequality here is actually a consequence of this weak convergence here, that the bulk energy of the Mumford-Shah functional is bounded by this term of the energy of the Ambrosio-Tortorelli functional, and this other lower bound inequality, which involves the surface energy part. So the first inequality, which is here, is actually an algebraic inequality, because you just apply the classical inequality, a squared plus b squared larger than 2ab. Okay, so it gives you that this term is bounded from below by grad v epsilon v minus 1. Okay, and this is exactly the gradient of the function w epsilon. So this inequality here is algebraic. Okay, and of course the difficult part, which is the difficult part of the lower bound in the Ambrosio-Tortorelli theorem, is this inequality here. Okay, so there is nothing new at this stage. It was just to start the asymptotic analysis. Next comes from our first assumption, our main assumption on which our result is based, is that not only we assume a boundedness assumption on the Ambrosio-Tortorelli functional, but also a convergence of the energy. This is our main assumption with which we are going to work, and so I'm going to comment about that maybe in the end of the talk. And thanks to this assumption, we can improve this weak convergence result, which are stated here, into essentially strong convergence. So the coupling term now, V epsilon, grad epsilon, okay, will converge not only weakly, but now strongly in L2 to the approximate gradient of U. And the jump set arises as the weak limit of the variation of the gradient of V epsilon. Okay? And there is a fundamental property which is called the equipartition of the phase field energy, which tells you that in the phase field energy, so you have two terms, these two terms here and here, and equipartition of the phase field energy tells you that both terms have exactly the same asymptotic weight. So in the L1 sense, epsilon grad V epsilon squared, so this term is equivalent, so in L1, to this one. Okay? So this is because if you go back to this lower bound inequality, when you assume the convergence of the energy, it tells you that all the inequalities that you have here are equalities. So in the basic inequality a squared plus b squared larger than 2ab, it tells you that a should be equal to b. So this is what I'm saying here. And in addition, since the grad of W epsilon consists in 2ab, it gives you, in addition, that the gradient of W epsilon, again, in the L1 sense, should be equivalent to 2 epsilon grad V epsilon. Okay, so this is the equipartition of the energy. Okay, so now we can proceed our asymptotic analysis. And to do that, we need further information on the solutions of the critical point of the Ambrosio-Tortorelli functional. So this is a regularity result that we prove with Vincent and Rémy, which tells you that in the interior, your solution is of class C infinity, as smooth as you want, and up to the boundary, you have all the regularity that you want, provided you do suitable assumptions on your data, which is the regularity of the domain and of your boundary data. So this is an expected result, although it has not been stated and proved before. And this regularity theorem allows us to take a particular test function in the system of PDEs satisfied by U epsilon and V epsilon. So you fix a vector field capital X, okay, compactly supported in omega, and you take these two test functions as test functions in the PDEs. So now that U epsilon and V epsilon are smooth, these are C infinity functions compactly supported in omega. You take them as test function. You perform various integration by parts, so I skip the details. And here is the expression that you obtain. Okay? This is the expression. So this is a quantity that I call delta AT epsilon, so which is some kind. This is exactly actually what you would obtain if you would have performed inner variations of the Ambrosio-Tortorelli functional. So again, you can see two terms in this expression. A first one, which involves the gradient of U epsilon, and the second one, which is related to the phase field part of the energy. So the first one, thanks to our previous result, which is rewritten here, so this term is the first term here, easily passes to the limit thanks to our strong convergence. V epsilon grad U epsilon converges strongly, so I can easily pass to the limit in this expression, and I get this one, which is exactly the first term which appears in the inner variation of the Mumford-Shah functional. So if I come back several slides before, this is exactly this first term here. So we are happy, at least we recovered one term in the inner variation. And of course, as you can guess, the difficult one is this one, because it is the one which involves the jump set, the sharp interface. And so it will arise as a limit of this term, but to do that, you need to work a little bit. So this term, this second term, I rewrite it here. This is this term. And now I will use my the statement on equipartition of the energy. So there are several steps. So in the first step, from passing from here to here, is just saying that this term, thanks to the equipartition of the energy, is equivalent to this term. This is what I wrote here. Okay? So this term, so the grad V epsilon squared comes with a factor 2, what I put in factor here. Okay, it factorizes as well the first term with the tensorial product. So here I used this part of the equipartition of the energy. The second equality here is there is nothing because I'm just factorizing by grad V epsilon squared. Okay, I did nothing. And from passing from the, I have some troubles to see where is the pointer. Okay, to pass from this term to this one, what do I do? So I first observe that by this definition of W epsilon, if I compute its gradient, the gradient of W epsilon is V epsilon minus 1 times the gradient of V epsilon. Okay? So it means that the gradient of V epsilon and the gradient of W epsilon are parallel to each other. Okay? So I can replace, so these are exactly the directions. I can replace the direction of the grad V epsilon by the direction of grad V W epsilon. Okay? And now there is this factor here that I replace by the gradient of W epsilon, and it comes from my second statement in the equipartition of the energy. That 2 epsilon grad V epsilon squared is equivalent in L1 to the modulus of the gradient of W epsilon. And here is the final expression, okay, the expression that I get at this stage. Okay? And now I recognize a so-called varifold structure for this phase field part of the first variation. So let me explain in a few words what is a varifold. So in this context, so we want to recover information at first order for a geometric object. Okay, so when you have a set, you can associate to this set the measure concentrated on this set. Okay? Think of a smooth surface. You can identify, in some sense, this set to the Hn-1 measure carried by this set. But when you want to recover information at order 1, it is also natural to encode informations on the tangent plane to this set at every point. And this is what makes a varifold. So a varifold will be a measure which will be defined on the cross product of omega, which stands for the spatial position of your object, but also on n-1 dimensional hyperplanes of Rn that I call Gn-1, so the n-1 Grassmannian if you want, which represents all tangent planes, and I will identify this set, as is usually done in this type of theories, to projection matrices on n-1 dimensional hyperplanes. And all such projection matrices can be written as identity minus E tensor E, where E is a unit vector orthogonal to the hyperplane. So a varifold is a measure on this product space. So it encodes information on the spatial position, but also on the tangent planes. So here, I will define a varifold, so a measure on this product space, capital V epsilon, by looking at its action on a test function defined on omega cross Gn-1, and I integrate over omega my test function, evaluated at the point x, and the projection matrix onto the hyperplane of Rn orthogonal to the vector grad W epsilon. So this is a tangent bundle which depends on x. I integrate it with respect to the measure mod grad W epsilon dx. Okay? So this is a varifold. This is such a measure. Okay? This is a definition. So with this definition of V epsilon, I can rewrite this last expression that I obtained with my small computation as the integral with respect to my varifold, capital V epsilon, of the function minus a grad capital X of x. So my test function phi of x a here is just minus a scalar product gradient of capital X of x. This is the test function that I use to rewrite this expression like that. So I did nothing. This is just another way to rewrite the same thing. Okay. So now, why is it helpful to rewrite things like that? It's helpful because V epsilon, almost by definition, is a bounded measure in this product space. So up to a subsequence, it will converge to a limit measure, capital V, which is what it is. But the idea will be to try to get information on this limit measure, enough information, at least, to be able to pass to the limit in this term here, this one. So capital V epsilon converges to some V. But then I have information on what is called the mass of the varifold. So this is this quantity that I write between double bars. Here, this one. So the mass of a varifold is nothing but the projection of the measure capital V epsilon onto the spatial variable. So what does it mean? It means that in the definition of the varifold here, it consists in taking test functions which are independent of the matrix variable. Okay, so it will be the integral of phi of x modulus grad W epsilon dx. So the projection of capital V epsilon on the spatial variable, the mass of capital V epsilon will be just the function, if you want, because it is a function, modulus of grad W epsilon. Okay? But I know, and it was a consequence of my assumption on the convergence of the energy, that this measure converges to the Hn-1 measure of the jump set. This is what is written here. And it's not difficult to see that the mass of a varifold, when you have a varifold which converges to a varifold, the mass will converge to the mass. So the mass of the limit varifold is exactly the Hn-1 measure of the jump set. So we have an additional information on the limit varifold capital V. It's not anything. It is a measure on the product space whose projection onto the spatial variable is the measure of the jump set. Okay? And when you have a measure on a product space and you know one of its marginals, you can disintegrate this measure, okay? And it gives, with respect to its projection, and it gives you the existence of a family of probability measures, capital Vx. So these are measures on Gn-1, parametrized by small x. This is like Young measures, if you want. And the action of the varifold capital V on a test function consists in first integrating the measure Vx with respect to A, and then integrate what remains with respect to the Hn-1 measure of the jump set. Okay. And now I can pass to the limit in the term, so in the previous slide, in this term here, and it gives me the following expression. And the idea to identify this limit expression is to identify what is inside the parentheses here, which is the first moment of the measure Vx. Okay? So this is something which only depends on x. And I give it a name. I call it A bar of x. So once I identify this matrix, it is a matrix, I am done. So this will be done using a blow-up analysis, similar to what did Ambrosio and Sonner in the Ginzburg-Landau context. And maybe I should, I have up to 4, right? So I have 10 minutes, perfect. So there are, first of all, several algebraic properties that I can prove on this matrix, capital A bar, yes. So we can quite easily prove, so maybe it's not obvious, but it's not difficult, that this is a non-negative matrix, okay, that its trace is equal to n-1, n is the dimension, and that the spectral radius of this matrix is equal to 1. So think of dimension 2, maybe to simplify ideas, but what I'm going to say all in any dimension. In dimension 2, when you have a non-negative matrix whose trace is equal to 1 and whose highest eigenvalue is equal to 1, you have two eigenvalues which are 0 and 1. Okay? So it means that, at least in dimension 2, by this algebraic argument, capital A of x at every point is a projection matrix. It is a rank 1 matrix, so it is a projection matrix in dimension 2. So you can write it as the identity minus E tensor E. So E is a unit vector which depends on x. So there is a further argument which tells you that you can generalize this argument to any dimension. And so capital A of x is a projection matrix. And the blow-up analysis, when you perform the blow-up analysis, you will show that in the varifold will converge to an elementary varifold, which will be of this form. It will be a tensor product between the Dirac mass at A bar of x0, so x0 is the point at which you are performing a blow-up, tensor product with the Hn-1 measure carried by the tangent plane to the jump set at x0. Ju is a rectifiable set, so at almost every point it has a tangent plane, an approximate tangent plane. And so this is a varifold because A bar of x0 is a projection matrix. And this limit varifold turns out to be stationary, which means this. And a stationary varifold satisfies the so-called monotonicity formula. So I'm going fast now, just trust me. Which tells you that you can identify what is this direction E of x. And this direction is necessarily the normal to the jump set at the point x0, or the normal to the tangent plane, which is the same. So E of x0 is a normal, so you have fully identified your matrix A bar of x0 to be identity minus the normal tensor the normal. And at this stage, you are done because you have fully identified your matrix. You plug it into this expression, and you put everything together. And here is the final result that we get. So I'm considering actually a Dirichlet problem with a Dirichlet boundary condition. So we need to assume a suitable regularity assumption on the boundary of omega and on the boundary data. Once we have such assumptions, we have some regularity on the critical points of the Ambrosio-Tortorelli functional. And the first statement is the following. So if the Ambrosio-Tortorelli functional is bounded, so up to a subsequence u epsilon will converge to a function in SBV2 whose approximate gradient is divergence free. So forget about that. But if further you have convergence of the energy, then the limit function u will be a critical point of the Mumford-Shah functional, which means exactly what is written here. So if you take test functions which are completely supported in omega, you get 0 here. To account for the Dirichlet data, you should take test functions which are not necessarily 0 on the boundary, but tangent to the boundary, which gives you some lower order terms here that I don't write explicitly. And so the critical points of the Ambrosio-Tortorelli functionals will converge to critical points of the Mumford-Shah functional. So actually, our result is stronger in the sense that we not only prove this, but we prove the convergence of the first inner variation of the Ambrosio-Tortorelli functional to that of the Mumford-Shah functional, as well as the second inner variations that I'm not defining explicitly. And in particular, it tells you that if you start from stable critical points, you end up with stable critical points. Okay, so just a last comment before, which will be actually my conclusion. So, is this result empty or not? So, I mean, can we ensure that this condition is sometimes satisfied, the convergence of the energies? So, this is an assumption. So, I'm not pretending to be able to always have it, but actually, this is true for global minimizers, because by gamma convergence, we know that the minimal energy converges to the minimal energy. So this is true for global minimizers. Okay? And we have performed a one-dimensional analysis similar to that of Frank Forley-Serfati, but with our set of boundary conditions. And we have proven that in the one-dimensional case, this is always true. We always get the convergence of the energy. And in the one-dimensional case, we further prove something stronger. We prove that even if we start from a critical point of the Ambrosio-Tortorelli functional, which is not a global minimizer, then the convergence of the energy is ensured. Okay? And so our result applies as well. Okay, so this is the end of my talk, and I thank you for your attention. You mean the least regularity that I need? No, you don't. But we do have C-infinity regularity in the interior. This is for free. I guess. So what I need, actually, the only assumptions that I need is here, actually, to have enough regularity in such a way that this is a good test, this is an admissible test function. So I need this to be in H1, 0. So the least regularity is that the gradient of that U is in H2 log. Okay. Yeah.
Thank you for the talk. In order to be sure that the limiting point, the assumption of convergence of n.
Yeah. So in the 1D case, it is true. In the higher dimensional case, so by analogy with, for instance, Hennenfent, we would expect that this is not always satisfied. And what happens for the Hennenfent is that there can be some multiplicities which appears, which makes fail this property. So we don't expect this to be true always. That would be great, that to be able to perform an analysis similar to this one. That is first to get essentially strong convergence on the bulk part and to get rid of this part and then to deal with the diffuse part. But I don't expect this to be true. I expect that there is some interactions that cannot solve the problem one after the other. I don't expect this. But I can hear you.
So you're looking at one of the.
Yeah.
That's
yes.
Over this.
The L infinity between 0 and 1, this is not relevant. What is relevant is that it is bounded in L infinity.
No, but if you had
a yes, you mean with the modulus just?
then
I would expect this to be true again, although this is not differentiable, so it might cause some technical difficulties, but I would expect the result to be true for a large class of potentials here, or some W of V. But we did it for this specific one.
a question?